In this video, we will focus on surface integrals. We will be using very similar techniques as we did in the previous video when changing integration variables. So I highly recommend that you watch that video if you haven't. A surface is an object with an area in three-dimensional space. This is the region we're going to integrate over here. The direction of the surface is given by the normal vector, which is perpendicular to the surface at every point. To give an example of what the surface integral could be, consider the following. You want to paint the surface in the figure. Assume that we are painting some pattern on it, which means that we use different amount of paint on different positions. We can therefore assume that the amount of paint needed is given by some function f, which depends on the position. With these assumptions, how do we calculate how much paint we need? This is an example where we need to integrate the function f over the surface S. For this particular case, we do not need to know the direction of the surface, only its size and position. The tricky part here is that we are doing a double integral, but the function and the surface depends on three coordinates, x, y, and z. If you remember line integrals, the trick we used was to introduce a parametrization and write that x, y, and z are functions of some parameter t, which we used as integration variable. We will do something similar here, but introduce two parameters u and v, which describe the surface. These are the two parameters we want to use as our integration variables to solve the double integral. To illustrate this, I will pick the xy plane as our integration variables. This means that parametrization simply is that u is x and v is y. The next step will be very similar to what we did for substitutions in the previous video. We define one small step in u called delta u and one small step in v called delta v. This will create an area element, which is the one we want to use for our integration. However, our integration surface is not the red rectangle, it's the blue surface. Hence, our area element should be on this blue surface. The idea here is to look at what happens on the blue surface when we take small steps in delta u and delta v. This would create the following two vectors. Then we can draw the surface element delta s generated by these vectors. This is the actual surface element we should use in the surface integral. If I let it move around on the surface, we can notice that while the area of the red rectangle stays the same, the surface element delta s on the blue surface varies with the position. The next step is to find the area of the surface element delta s. Start by looking at our step in the u direction delta u. We did show in the previous video that this will give the following vector b1 after the transform. Looking in the figure, this is the green vector on the surface. We basically take the partial derivative with respect to u as scaling factor. Now, remember that the position vector r is x, y, and z. Here, x, y, and z are functions of u and v if we assume that r is on the surface. If we compare these, we can see that b1 actually is the partial derivative of the position vector with respect to u multiplied by delta u. Hence, instead of b1, we can write dr du times delta u. Moving to the second vector, when we take a small step in the v direction, this will follow the same pattern. All we need to do is replace the derivative to be with respect to v and multiply with delta v. This means that our two vectors on the surface are dr du delta u and dr dv delta v. The next question is, how do we calculate the area once we have two vectors for the size of a parallelogram? I hope you are thinking about the cross product when you see these conditions, as the cross product gives the area of a parallelogram with the vectors of size, with the direction of the normal vector of the surface. Hence, write n hat delta s equals the cross product between the two vectors on the surface. As delta u and delta v are scalars in this equation, we can put them outside the cross product. And in the limit when delta u and delta v goes to 0, we can replace delta with the d. In our particular example of painting the surface, we only care about the size of the element delta s, not the direction. Therefore, we can drop the direction and write it as the length of the cross product instead. We continue and update expressions for the integral. We can start by rewriting that f is a function of u and v instead. Then we can insert our surface element ds. And we have the expression for how to solve the surface integral when integrating over u and v. Let us show an example. Say that z is 2 minus x squared minus y squared, which is the surface in the figure. The limits are that both x and y goes between -1 and 1. The next step in the general method for solving these problems is to rewrite equations using the parametrization. It may be a bit silly here as u is x and v is y, but let's do it anyway to illustrate the method. We continue and update the position vector r by writing it in terms of u and v. We simply get that r is u x hat plus v y hat plus z of u and v z hat. Next is to look at the vectors. Start by dividing with delta u. And the same for delta v. As x is u, this is du, which is 1. As y is v, this is du dv, which is 0, as the partial derivative considers u a constant. For the second vector, x is u, hence this is du dv, which is 0. As y is v, this is dv dv, which is 1. Let us look at the cross product. Start by writing it element by element. All these 4 are 0, as we recently saw. All these are 1. This is as long as we can go without using the equation for z of u and v. Hence, all cases where z is a function of x and y will follow the same path until this point. Now, we can continue and solve for the specific function we have been given. The z du is minus 2u. And the minus cancels. The z dv is minus 2v. And the minus cancels. Finally, we can use the Pythagorean theorem and write this as a square root. To solve the general integral, insert this into the equation for the integral. Unless f of u and v is a very simple function, this will likely be very hard to find analytical solutions for, as we need to solve a double integral where both u and v are inside the square root. But if you can rewrite it to this point, you can use a numerical solver for double integrals and get a solution. Therefore, I think the most important part for this video is to learn how to rewrite surface integrals to double integrals. With this, let us leave this example and show another parametrization. Let's say we want to integrate the surface of a sphere. This is commonly done using spherical coordinates, where we assume that the radius is constant. The position vector is the following, where it is the two angles theta and phi that we want to integrate over. Quick recap of spherical coordinates. Theta is the angle between the position vector r and the z-axis. Phi is the angle between the x-axis and the projection of the position vector on the xy plane. Let the black dashed line represent a small step in theta direction delta theta. The orange dashed line represents a small step in the phi direction delta phi. These will create a surface element as shown in the figure. By changing the value of phi, we can see that the element appears to keep its area constant. If we change theta though, we can see that the surface element changes its area. We can therefore expect that the area element depends on theta. To calculate this, start by noting that the r hat vector is the vector r divided by its length, r. Next, let us calculate the two vectors we need for the cross product by differentiating with the two angles. Start with the dr d theta. First, differentiate the x-coordinate with respect to theta. Continue with the y-coordinate and the z-coordinate. Do the same for the second vector dr d phi. Start with the x-coordinate with respect to phi, then the y-coordinate. The z-coordinate does not depend on phi, hence no contribution. Now, write the expression for the cross product component by component. As z does not depend on phi, these are 0. Insert expression for the first term and the minus cancels. Write these as r squared. Insert expression for the second term. Cancel the minus and combine to r squared. Insert the next term. And combine. Insert the final term. The minus cancels. Combine these. These are a common factor. And this is 1. R squared sinus theta is included in all terms. Finally, we can identify this vector as the vector r hat. This is an example of how we can use the equation to calculate the surface element in spherical coordinates. Just as in the last video when we calculated the volume element through the Jacobian, I said that there is an easier way to do this, and the same applies here. That we could have used that spherical coordinates is an orthogonal coordinate system, hence the angle in the cross product is 90 degrees. I will show how to do this in later videos. Let us move on to another case and study how we can include the direction of the surface. In the next example, which comes from fluid mechanics, we are going to calculate the force due to pressure. The hydrostatic pressure is given by the density ρ times the acceleration of gravity g times the depth below the water surface. What is the force on a surface submerged in the fluid? As the force is the vector, add the vector notation to F. Our function in this case will be minus the pressure. The minus comes from the definition of pressure. I will cover this in more detail in my fluid mechanics videos. This time, the direction of the surface will be important, as bring back the normal vector. We simply use the full vector of the cross product to get the normal direction. Next, let us reuse our surface from the first example. The pressure is pushing against the surface, which is opposite to the normal vector. That is why we included the minus sign in the integral. We use the same position vector as before, and the same z function, and the same parametrization. The function for pressure is the one given in the example text. We want to have p as a function of u and v for our integral though. All we need to do for this is to include that z is a function of u and v on our surface. It's important to remember that z should be the value on the blue surface, which varies with the u and v as you see in the animation. We can then insert equation for z and simplify. Now it's time to start solving the integral. Insert expression for the pressure. We did calculate this cross product earlier in this video. Use that expression. Let us solve this integral one direction at a time. Start with x. Distribute u. Write the double integral as one integral over u and one integral over v. Let us solve the inner integral. Note that u squared and u to the power 4 both get the same value when we insert 1 and minus 1. Hence both cancel, and the whole integral is 0. We could have seen this in the step before by noting that it was antisymmetric. Or by symmetry of the original problem, we could have assumed that the force in the x direction should be 0. Next, set up the equation for the y direction. Distribute v and write it as two integrals. Again, we can see that the integral is antisymmetric, but this time with respect to v. Hence the integral is 0. Finally, the z direction. Write as one integral over v and one over u. Integrate with respect to u. This time we got a symmetric integral, which is 2 times the expression when u is 1. Place 2 in front. And combine these. Integrate with respect to v. Once again, it is symmetric and we can insert the limits. Place 2 in front and simplify. This is the final expression for the force due to water pressure, which only got the z component due to symmetry. We can see that in this case, when we included the direction of the surface, we got much easier integrals. This is due to that we no longer have the square root to deal with when finding the primitive functions. If you want to see an example of a pressure integral over a sphere, I will include that in the video on spherical coordinates. To summarize, when we integrate with the direction n hat included, we got 3 integrals to solve, 1 for each direction. Moving on to our next topic, which is integrals of vectors. The first case is a vector integrated over a scalar element ds. This would be as our first example with the paint, but we do 1 integral for each vector component. This one is not that common though. The next case is when we have a vector function and include the direction of the surface as well. Similar to line integrals, this gives us 3 options. The first is a dyadic product with the direction vector. This one would require that we solve 9 separate integrals, 1 for each element in the matrix. If we instead want to use the cross product, this is the off-diagonal elements of the dyadic product. This gives the following 6 integrals. Finally, the most common one is when we use the dot product between the vector and the normal vector. To give an example, assume that you have a constant flow velocity v. What is the flow through the surface? This one is solved using the integral of the velocity dot n hat over the surface. Let us start to solve the integral. Assume that the velocity has an arbitrary direction and write it on component form. As we use the same surface as before, we still have the same cross product. Now we can perform the dot product before we calculate the integral, which simplifies our solution. We write the integral in terms of v and u. Carry out the inner integral. We can see that the vx term is antisymmetric with respect to u and will be 0. Remaining terms are symmetric. Solve the second integral. This time the vy term is antisymmetric and becomes 0, while the vz term is symmetric. The final result becomes 4 times vz. Note that 4 is the area of our integration region, or the red rectangle in the figure. Let us move to a different topic, which only partly is related to surface integrals. This is how to move the derivative inside the integral for double and triple integrals. Let's have a repetition of the one-dimensional case first. The derivative of an integral here has 3 different contributions, which we'll see in the figure. We draw a graph of the integral of f of x and t, where x goes from a to b. We can also add that the function value at the start is f of a and t, and at the end is f of b and t. The first term will represent that the function changes in value with respect to t. The second term is if you have a time dependence in the lower limit a. And the final term is if you have a time dependence in the endpoint. I'm also going to rename the a dt to the velocity of the boundary of the integration curve c. To write the boundary, we use the same symbol as for the partial derivative before the c. We can also write that the b dt is the velocity of the boundary at point b. Now, it's time to move to the double integral. Note, this is the ordinary double integral in two-dimensional space. This means that this time the red rectangle is our area of integration. And the blue surface represents the function value of f of r and t. Start by adding the partial derivative term inside the integral. This would represent changes in the value of the function f with respect to t. Next, let's add a velocity to the boundary of the area A. If the boundary moves, we would also change the value of the integral. Of course, all boundaries can move. Hence, add the normal vector around the full boundary. Now we can write the change in the integral due to moving boundaries as the closed integral of f of r and t multiplied by the velocity of the boundary dot n hat. This expression will allow us to have motion for all boundaries, and the velocity can be different depending on position. To answer the question why we need the dot product with the normal vector, consider the following case. Let all boundaries move in the x direction. We can now see that the two sides that will have the normal vector in the x direction will have parallel vectors for the dot product. This means that only the contribution from these two will change the value of the integral, as we see in the animation. If we move to a volume integral in 3D, it is about the same, but this time the boundary integral is our surface integral over the closed surface of the boundary. Later in the fluid mechanics classes, we will work more with moving boundaries when we talk about control volumes. This is the final case for this video. In the next video, we'll work more with closed surface integrals and volume integrals when we talk about Gauss theorem. Thank you.